what you don't need to. Again, it's up to you guys. You guys are young adults at this point. You guys should know what you need. So here's what we have. When we're doing some of our rate of limits stuff, there's a few vocabulary terms that you need to know. Average rate of change, instantaneous rate of change, secant line, tangent line, distant, and something called displacement, which is not adjusting. Why are you not? And of course it's frozen. Come on. All right, there we go. Okay, distance, displacement. So I'm going to be going over each of these. One of the things that's really important in AP Calc is, since you're taking the AP exam, you are going to need to know the vocabulary. You are going to need to know the way they say it. I'm going to try to keep my vocabulary, and a lot of the practice problems I'm pulling are just straight from the multiple choice or from the free response on the AP Calc exam. So you hopefully should be familiar with it by then. So average rate of change basically says over an interval, how much distance did you cover divided by how much time did it take you to do that. That's your super standard average rate of change. It's also called speed or velocity, that you've done a lot in algebra 1 and stuff. Should be super familiar. Instantaneous rate of change says at 35 seconds, how fast were you driving, or something like that. A secant line is basically, if you have a curve, it's a line that goes through it, which is very similar to when you guys did geometry. You guys had like a circle or something, you had a line going through it. That's a secant line. Tangent line is a line that touches at exactly one point. Distance is going to be how far you move given an interval. Displacement says from start point to end point, how far was that distance from your start point to end point. Nothing else matters. Now I'm zipping through it really quickly because I'm going to elaborate, but what I like to do is I like to kind of just throw everything at you once and then kind of go into it to prime it. So here's what we're going to do. Now let's kind of look at our rate of change. Here's the idea. You're driving to Mililani for some Black Sheep Creamery. It's 21 miles and you get there in 30 minutes. What is your average rate of change in terms of miles per hour? Now, most of you guys can do this off the top of your head. It's going to be 42 miles per hour, right? If you go 21 miles in 30 minutes, in 1 hour, you double that. So you go 21 miles per hour. Now, you know that your average rate of change is going to be 42 miles per hour. I'm going to write that down, 42 miles per hour. Now, the thing, though, is if I ask you what's your instantaneous rate of change, the reason that's different is I might say something at 17 minutes, how fast were you going? It's not like you were going 42 miles the entire way. You weren't driving 42 miles on the freeway, hopefully, and you weren't driving 42 miles like right next to your house as you're pulling out of your driveway. When you're doing average rate of change, all that doesn't matter. Again, it's an average. You're saying, okay, this is approximately how fast I was driving. Instantaneous rate of change, though, is very specifically saying, okay, at this exact second, how fast are you going? Okay, that's the main difference between average rate of change and instantaneous rate of change. Questions? Okay, excellent. Distance displacement is very similar. Same idea. You're driving to Mililani for some Black Sheep Creamery. It's 21 miles away from school. You start driving at 12:34. You get there in 30 minutes and get back to school to work on AP Calc at 1:21. How far was your displacement? Again, displacement says from start to end, how much did you change? You started at school. At the end of the day, you ended up at school. Your displacement was a grand total of 0. But when you're looking at gas, when you're looking at, okay, how far did my car actually move? How much did my odometer go up? That's where you look at your distance and you say, okay, I traveled 42 miles, really didn't move anywhere, but at the end, but that's how far I traveled. So again, distance displacement, that's the main difference. Okay, I'm assuming most of you guys should have got this. Just real quick, how many of you guys have seen distance displacement before because of like physics or something? Just like when I used to stream on Twitch. Ask a question, get no answers. All right, that's fine. Whatever. All right. So this is how it's going to look a lot more when you guys are doing your standard calc problems. Now, um, it's going to give you like a graph or something like this, and it's going to say a stone is thrown vertically into the air with initial velocity of 15 meters a second. The function for height in meters and time in seconds is given by h of t equals 1.5 plus, yeah, you guys can read it. Find the average rate of change between 0 and 3.158. Now, just to kind of let you know, if you're looking at the graph, this over here is about 3.158. I did the heavy lifting for you, so you kind of know what that is. Now, when you're finding average rate of change, in order to find average rate of change, all you do is it's just y2 minus y1 over x2 minus x1. Again, you guys should have kind of already knew this already. This is average rate of change. This is slope. Should be fairly simple. So if I were to ask you to figure this out, good luck. Okay, what I want to see if you guys can do is hopefully you guys have something to type with, like a computer for Desmos or some sort of online calculator, or you have a calculator with you. What I want you guys to do really quickly is figure out what is the average rate of change between 0 and 3.158 seconds for t. What is the average rate of change? Okay, figure that out, type it in the class chat. I'll give you guys about 2 minutes. All right, good luck. Okay, so I'm gonna give you guys a little bit more time, but how many of you guys do not know where to go in order to type something like this in? Like, you don't have any calculator with you. Again, please type in the class chat or something like that. If you guys haven't seen it, again, it's the text channel that just says class chat. This will be reset every class, basically. Okay. How are we doing? Like, are we getting there? Not doing anything? What's the deal? Now, the reason why I'm checking is because I'm trying to figure out how good you guys are with the technology you have now. And if you aren't good, then I have to give you stuff so that way you can kind of do some of these calculations, because a lot of these calculations aren't going to be really quick. This is actually a pretty easy one to plug into a calculator. Your numbers generally aren't going to be really nice, so I need to know what I'm working with. So that's why I'm kind of doing this. Again, I know I'm belaboring the point a little bit, but if you guys could either unmute or type in the chat on a scale of 0 to 10, how close are you to finishing? Finding the average rate of change, which is literally the slope. How many of you guys rounded? Because shouldn't have rounded. Did anyone do any rounding? No? Okay. Good. All right, so here's what we got. Now, here's the thing. A lot of you guys said that it seemed stupid that you guys were getting like a negative number, or like what the heck is going on. But let's look at this really quickly. Sorry, I know this is a little fuzzy, but here's basically what's going on. You're saying what's it called? 3.518, that's here. And we're saying at 0, which is like right around here. It's hard to tell exactly where it's like 2 or 1 or something. From here to here, my average rate of change, my ball starts off higher than when I end up. So that means that my average rate of change should eventually go down. And it just feels wrong though, right? If you're throwing a ball up, doesn't that mean that it's gonna, like, the velocity should be positive, right? It should make sense. But that's the thing when you're dealing with calculus. You're not dealing with quote unquote what makes sense off the top of your head. You're always looking at the context of the problem. Now, what it says is that it's thrown. Now, if you're throwing it in the air, you're holding it in your hand, and when it eventually hits the ground, it's on the ground. Where it starts is in your hand, where it ends is on the ground. What's higher, your hand or the ground? And you guys should know that the answer is your hand. Which is why at the end of the day, when it hits the ground, it's actually going to be lower than when it started. Does this sort of kind of make sense? We're doing all right. Okay, so whenever we're doing these types of questions, it's always a good idea to kind of see, okay, what makes sense? Let's double check. Don't just think, oh, we got a negative answer. Something must have gone wrong, and trying to figure it out from there. Now, this is again. Okay, sorry. This is again our average rate of change. We're saying, okay, what's going on there? Now, average rate of change sometimes makes sense, but sometimes it doesn't make sense too much. But again, it's all about how you use it. Now, if I say, okay, my average rate of change is like negative 0.47 or something like that, is that really going to help? Now, sometimes though, it's basically if I have this line over here, this blue line, it's like I just drew that. Is there any real difference between the average rate of change of this line and the rate of change of this, or average rate of change of this red line. Like, no, not at all. If you're taking from this point to this point, all average rate of change does is it says, okay, from start to finish, what's the displacement, right? How much did it move, and how long did it take it to move that way? And so because of that, really average rate of change doesn't give me too much. So always keep in the back of your mind that average rate of change is one way that we look at slopes. But average rate of change is really a bad way to look at slopes because it's just not very accurate. There's a lot of inconsistencies there. So we're going to talk about that a little bit more here. Now, if I give you a question that looks like this, it's the exact same start to our question, but it says, find the velocity of the rock at 1 second and at 2 seconds. Okay. I'm no longer asking for average rate of change. I'm asking for instantaneous rate of change, right? Obviously, at 1 second, if I threw it up, we can't just take that negative 0.47 and just like, okay, it's negative 0.7 here, negative 0.47 here, negative 0.47 here. We can't just do that anymore. We have to figure out what it actually is. Now, basically, the way that you can do that is, let's look again at this graph over here. What's going on is first is curving up, then it reaches its vertex, then it starts curving back down, so on and so forth. But what we're saying is at 1 second, 1 second is right around here, and it's right about here. We're saying how fast is it going? Now, when we're looking at rate of change, a lot of times we look at what's called slope, right? Slope is another word for rate of change in y over change in x. So we're saying, really, how much is x and y changing at this point over here? And that's where we basically look at something called the slope of the tangent line. This slope of the tangent line is the most critical part in all of calculus. 90% of calculus, or excuse me, maybe about 90. About 90% of calculus problems are built up around these slopes of the tangent lines, either finding the slope, finding an interpretation of the slope, or finding a slope given a more difficult problem, or going backwards and saying, here's the slope, can you find the original line? But these tangent lines, we're saying, okay, if I were to rest the line that were tangent on this slope at this exact point over here, if I know the slope of this line is something like, I don't know, 3 or something, again, I'm just totally pulling this number off the top of my head, we'll talk about it a little later. If I were to pull this slope here, then this here gotta be pretty doggone close. And what we're gonna find later on in calculus is that we're gonna say, okay, if you know the slope of the tangent line, you can find the slope of the line, or slope of the curve at that exact point. So this is how you find instantaneous rate of change, is by finding the slope of the tangent line. That's one of your most fundamental parts of calculus, basically. Okay, so far there's two parts that we're working on: your average rate of change and your instantaneous rate of change. Average rate of change, you look at the endpoints. Instantaneous rate of change, you look at the slope of the tangent line. I'll show you guys how to find that a little bit later, but for now we're gonna kind of move on. This is something that we're gonna touch on later, again, like I said, but we're just introducing it for now. Okay. Good job, Jasmine. All right. So here's what we're going to do. Now, let's look at this same problem over here. And we want to find the velocity of the rock at 1 second. Now, because as of right now, I haven't shown you how to find the slope of a tangent line, there are some ways to kind of figure it out. It's really, really kind of tricky. Instead, what we're going to do is we're going to look at something called slope of the secant lines. Slope of the secant lines. Now, as I mentioned previously in the vocabulary, a secant line is a line that crosses through your curve at 2 points. It's very, very similar to when you guys were doing geometry and you had secants versus tangents versus chords, all of that fun stuff. Now, basically, what we want to do is we're saying the same thing. Okay, at 1, if this is 1 over here, what is the slope of my tangent line? But really, it's kind of hard to figure out the slope of the tangent line at this point over here. So instead, what you're going to do is you're going to find the slope of the secant line. And the way that you're going to do that is you're going to say, well, I might not know what this tangent line is per se, but what if I took this point that's on here? And I know how to figure this out because I know all of the points of this graph all I do is just plug in my x and find my y. So all you're going to do in order to find this point over here, like this could be something like 1 comma 11 or something. Again, I'm just pulling a random number. And this number here could be something like 0.999 comma 10.995 or something like that, right? Now, if you know that that's what it is, then what you can do is you can make this secant line. And as you can see, it's actually not the tangent line. It's not the instantaneous rate of change, but it's kind of close. Like, it's not terribly far off. And especially if you zoom out a little bit, it's really not bad if you look at it from far away. And that's kind of what we're going to be banking on here, is we're saying, okay, I might not know what the instantaneous rate of change is, but I can get pretty doggone close. I can get way closer than if I just take end to end and say, okay, it's like negative 0.47. So that's kind of the main idea here, is that what we're going to do is, in order to find instantaneous rate of change, in order to approximate instantaneous rate of change, we take average rate of change over a really tiny interval. The smaller your interval, the closer your approximation is. Like, for example, if you're trying to find on this one, again, I'm going to just keep putting it here at 1. And if you're trying to find out what it is here, if you took this point here and this point here, then guess what? You're getting a pretty doggone close line. If you took this point here and this point here, you're not getting quite as close of a line, but you're still getting closer than you would have if you got like your endpoints. Right? So that's the main idea here, is when you're finding instantaneous rate of change, you can use secants and you just kind of make your intervals as close as possible, which is why I wanted to make sure you know how to use your calculator well, because it's one thing to take your interval from 0 to 1, but it's so much more accurate if you can take your interval from like 1 to 1.000001. And if you are able to figure that out, it makes life so much easier. So here's what we're going to do. What I want you to do is I want you to find the average rate of change of this on the interval 1 to 1.001. Okay, so again, I want you to do it just like you guys did it previously. I'm going to be doing it in live time with you guys. I'll tell you when I'm done, and once you're done, I want you to type in done, because what I want you to do is I want you to see how quickly it takes me to do it, and I want to see how long it takes you guys to do it, so we can see if we can speed this up, because again, calculator use is going to be a part of your AP exam, and if you're getting bogged down on your calculator use, it makes everything else way more difficult. Before we get started on that though, do I have any questions on average rate of change, instantaneous rate of change, or like kind of the format of what we're going over right now? Again, all I'm doing is I'm throwing in some vocabulary at you, trying to get the main concept down, and we're just moving forward with that. Any questions so far? Okay. So since most of you guys don't have any questions, try to see if you can figure out what the average rate of change is of the rock on the interval 1 and 1,001. Now I'm going to do this from scratch on a separate browser, and then I'll tell you when I'm done. Hopefully you guys can beat me, because you guys had a little bit of a head start, but if not, we'll just see how long it takes. And again, this is just for you guys to kind of figure out, okay, how long would it take me to do something like this so we can speed up. All right, let's go. Done. Good, good, good. A lot of you guys are relatively quick. Just that first one seems to have taken you a long time. Okay, please type out what you guys got inside the class chat and we'll see how we did. You guys are all so polite. All right, cool. Y'all are so polite. All right. How we doing? Doing okay. Doing good. Okay. So one of the nice things about having a class like this is if you have any questions, you can just throw it up. I might not stop to read your question right away, but I promise I'll get to it eventually. All right. Last thing before I move on. Some people said they like having my face in this little bottom square over here. Some people said that they prefer not having it when I was doing my distance learning. Would you prefer having it here, or would you prefer having it like totally clean like this? Up to you guys. What do you guys think? Dang it. Okay, I guess we're leaving my face in for now. All right, so okay, that's kind of how we're going to be doing average rate of change. One of the most common questions that you guys are going to be doing is, again, rate of change types of questions. If you're asked to approximate a rate of change using an interval, this is how you do it. You just take average rate of change. Instantaneous, again, though, you use your tangent line. So far we've covered all of our major vocab terms. So this is like the first half of the lesson. All of this over here is just building up to this idea of something called derivatives, where we're finding what is the slope of the tangent line, how do we find instantaneous velocity of a specific curve. That's like, again, 90% of calculus is built around that, or like undoing that, or problems around that. Now, what we're going to do in order to do that, though, is this is still just an approximation. What happens if we, instead of going from 1 to 1.001, we went from 1 to 1.0001 or 1.0000001? Like, the closer we get, the closer our approximation gets. And so in order to do that, we actually built math around this to say, okay, how do we make it seem, so even though we can't take 2 points that are on top of each other, how can we make it so we can take points that are really, really, really doggone close? So that's how we get introduced to this idea of limits. Now, again, I was going to make you guys do this, but we're a little bit over time, and especially since that first one took such a long time, I was like, we're not going to do this. But if you look at this, your numbers are actually going to get closer and closer the more accurate or the smaller your interval is. So your goal is you want to figure out, how do we make sure that this interval is as small as possible? And that's where we're given something called limits. So let's look at this one more time before we move on. So this is another really common problem. It's almost exactly the same thing. It says this: given is a graph of Chile's internet users in millions given a year. This is called continuous data, just as a fun step. The reason it's called continuous data is because it grows continuously. What I mean by that is it doesn't magically jump. It's not just saying, okay, at the start of 2001, we were at 2 million. At the start of 2002, we're at 3 million. And it doesn't just jump, and it doesn't just randomly make lines, but it's saying, okay, halfway through 2001, this is how much it was. Halfway through 2002, this is how much it was. So that's why it's called continuous data. Do you need to know that? Not necessarily, unless you're taking stats, which is important because all of you guys should be taking stats so you know about the world. Take AP stats. But that's kind of what's going on here. Now, here's what I want you to do. It says estimate the rate of change at 2003 in July, approximately where the dot is. Now, the reason you know it's in July is July's halfway through the year. That dot is halfway through 2003, 2004. So what I want you to do is estimate the rate of change for this. Now, I'm going to zoom in on this over here so that you guys can see it a little bit better. I'm going to subtract my face so that it's easier to see. Now, what I want you to do is estimate it. Now, as best as you can, just try to estimate it. I know that you're not given perfect numbers, but just use whatever numbers that you're kind of approximating. And then I want to see what all of you guys get. So again, take about 3 minutes to type this out. Then after you're done typing this out, it should take quicker than that. Just type in whatever your answers are. You should not be having the same answers. Okay, you should not be having the same answers. So, type it out. Let's go. What do we got? Try it out. Okay, the question was, at 2003, what was the rate of change of internet users? In July of 2003, or approximately where the dot is. Sorry, I know I zoomed out of the question. It's just because I feel like it's easier to kind of read if this is fully expanded. But approximately where the dot is, what is the instantaneous rate of change of internet users? What is the instantaneous rate of change of internet users? Again, I'll give you about 2 minutes. Let's go try it out. Okay, good. A lot of us are getting like 0.29, 0.25, 0.38. A lot of us are getting numbers that are really, really similar to that. That's totally fine. Now, the reason why I said you're all going to get different numbers is because there's so many guesses that you're making. Like, what even is this point over here? Like, is this, like, in my mind, this is 2003.5, comma 4.15. Like, that might have been it. Some of you guys might have said it's 4.1, and some of you guys might have said it's 4.2. Some of you guys might have gone from here to here. Some of you guys might have gone from here to here. There's a lot of different options and a lot of different guesses that you guys could have done. But again, if you're finding what is the rate of change, like it says, what is the rate of change approximated where the dot is, or estimate the rate of change. Whenever it says estimate rate of change, that's just kind of a hint for saying, hey, find the slope as best as you can. Sometimes it's going to be as simple as doing rise over run and just finding 2 points. Sometimes it's a lot more fun. Okay, next, question number 2. It says, does the rate of change increase or decrease as t increases, or is it just depending on t? Meaning, if I'm looking at this graph over here, is my rate of change constantly increasing, constantly decreasing? Now, I'm not saying is my rate of change positive or negative. That means if my rate of change over here, some of you guys said was 0.25, that means if I took my rate of change here, it's going to be bigger than 0.25. So do you think it's constantly increasing, decreasing, or staying the same? Now, this is something I kind of want to try. So here's what I want you guys to do. I want you to pick a study room, numbers 1 through 5, and you can't have more than 6 people in a study room. Come up with an answer and then type your answer here after. But go in a study room. You guys have until 1:57 to come up with an answer and then come back. Okay, let's try it out. All y'all go to study room 1 since you guys are there. But just, yeah, talk it over. Go for it. I mean, you can talk about it with me, but I figure that's more embarrassing. So it also gives me a chance to see who's paying attention. So if you go under general, there's something that says Maury's office. And under that says study room 1. So click study room 1. Yeah, voice channels. So just like how you're looking at the text channels, you should be able to look at, there's voice channels under it. So if you scroll all the way down past the voice channels, down past the text channels, it should say voice channels. Yes, sir. Okay, so we're saying at this point over here, according to the information given. Good question, but according to the information given. So just the graph. Yes. Okay. So again, the goal of being in this chat was so that way you guys can talk about it. So again, come up with an answer. Does it increase, decrease, or is it depending on the t? So you guys should be conversating. Good luck. Okay. Sure. All right, we'll wait till everyone gets back and then just type in your answer. Excellent. All right, now as you guys are joining back, hopefully you guys came up with an answer. Try to make one person per each group type what you think your answer is, and then I'll ask them to explain why. So again, make sure you pick your spokesperson wisely. So ask them, and I'm just gonna ask them why. Now again, I might not always do this. The reason I'm doing this now is I'm trying to see how this works, like how I can get feedback from you. I'm just testing like the limits of Discord and how this works as a class. So I know I'm being a little wonky right now, but I kind of want to just try this out, see how it's going. All right. So again, once you have your answers, then have one person type it and be prepared to explain. So you're gonna verbally explain it. I'm gonna call on you, and you can verbally explain it. Oops. Okay. I should have 4 answers because I have 4 groups. So I have 2 so far. Alrighty. So here's what we got. Again, if you have not done so already, if your group has not typed it in, please type in what you think your answer was. We have 2 people who think it's decreasing, 3 people who think it's decreasing. So first off, Kaiki, do you mind explaining to us why does your group think it's decreasing? Mm-hmm. Okay. Excellent. Anton, you have anything to add? Okay, Akiko? Okay, no worries. All right, so again, that's basically it. Now, the reason why I wanted to bring that up, and that was very good of you guys to notice, is when you're doing tangent lines. Now, I'm going to show you this. This is some like high-tech stuff over here, but basically, all you're going to do is if you look at this, you can get your freaking pen and just say, hey, if I was going to put this as a tangent line, what does it look like? And as you're following the curve, like what's happening to your slope, it's flattening out. This sounds really wonky and stupid, but I'm telling you, when I took the Calc 2 exam, like, or the Calc PC exam, I did that so many times. Like, you just get your finger, throw it on there, be like, okay, because sometimes it helps you visualize it. Being able to separate the difference between the number and rate, and eventually you're going to talk about the acceleration as well. When you're looking at those 3 different parts, being able to use things like pencils and just put out your tangent lines to help you. These are all tricks that are really, really helpful. But again, it's really good. You guys kind of got it. When we're looking at this, we're just saying, okay, if I had an imaginary slope at each of these points, what happens to it? And that's perfect. That's the exact visual that you guys want to do. Okay, now real quick, I'm not saying I'm going to do this often, but as far as splitting up into groups and just having a quick talk, was that relatively smooth? Was that relatively helpful? Because I think it's nice to do that every now and then, instead of just having me talk for like an hour and a half to 2 hours. But if it's really clunky, I don't want to have to do it often. But how was that for you guys? Again, if you guys can just chat real quick, because again, I'm trying to calibrate to what I can do on here. Okay, most of you guys who are typing, all 3 of you, seem to enjoy it. But again, just keep typing, even if I keep moving on, but just tell me what you think about it. One thing I probably would do in the future is I would pre-assign you guys to groups, like study group 1, 2, 3, 4, 5, 6, or whatever, and I would have you guys choose your group so you know exactly where to go to. Okay, some of us had technical difficulties, some of you guys thought it was good. Okay. Okay, again, just let me know, because like I said, one thing that I do want to try to do, especially since I have a lot of tech expertise at my disposal, I can try to make it as tailored to you guys as possible, and that's our goal here. Okay, moving on. So let's try another 2. It says this: find the average rate of change over the 4 years shown, and then in 2002 was the rate of, or in 2000 was the rate of holy moly, in 2002 was the growth of internet users rate of change greater than the average found in 3. Okay, was in 2002 was the growth of internet users greater than the average found in 3. Okay, try figure that out. Good luck. Go back into your groups. I'll give you guys until 2 o'clock to figure this out, and then swing back in. All right, we'll just try that one more time. Stick to the same groups that you were in. I'm gonna leave these 2 questions up. See if we can figure that out. I'll be right back. I'm gonna grab some more water. Okay, Rocky, can you please explain how you got your answers? Rocky? Mm-hmm. 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 Oh, so you compared from 2002 to 2003. Okay, sorry. I must have I wasn't clear about the question. It said greater than the average found in three. I meant like the average found in question three. Excuse me. That was my bad. No, that's fine. No. All right, Anson, you got a slightly different number. What did you? So what did you do? Okay. All right. Okay. What did you? What what did you use to approximate at 2002? Just out of curiosity. Oh, okay. Okay, thank you. Akiko. Mm-hmm. Okay, excellent. So I'll make sure to be a little clearer on that. Um, One thing that you guys can always do too is you can always just draw your. If you know your average, you're just taking it like that, and then you can always just zoom in and be like, all right, let's go check it at this point over here. What do we think? That's not the most scientific way, but if you want to, you can always just do it. If it's super obvious, you can just take a guess. And again, especially when there's no numbers like this, you can always explain and say, hey, because the tangent line at 2002 is greater uh, than the secant line connecting the two endpoints, it has a greater slope, then you can assume that the rate of change is greater. One of the things that they always do is they look for things like that. Like when you say tangent line, secant line, since these are calculus vocabulary, it sounds wonky that you said, hey, I drew the lines and it worked out. But on AP exams, they actually do have cases where they said if they use these words, then you have to give them points for it. So that's why it's good to kind of know what secant lines are used for, what tangent lines are used for. I know at this point I'm kind of beating a dead horse, but we're just, again, like I said, I really want to make sure that we understand context, because everything that we're doing from here takes this, builds upon it, and makes it slightly more difficult. Okay, I know we're getting about an hour in. We're about 3/4 of the way through. How are we doing? Any questions? Do we need a break, or are we good to just keep trucking through? I got about 25 more minutes left on the clock, assuming that we move through everything really quickly. Do you guys want to take a 5-minute break, or are you guys doing good? Okay, looks like most of us are doing good. If you need to take a break, that's totally fine. Just take a quick breather. You can totally come back and just ask your friends what's going on. We need to show any work if we use the pen on the lines. No, but again, you will have to explain. Like, for example, if I gave you a question like number four, I would ask you to explain why. And you could say something like, graphically, if I were to draw a tangent line at 2002, the slope of that tangent would be greater than the slope of the secant visually, or something like that. You don't need to say it quite that flowery, I guess, but you do need to explain. Almost all AP questions do come with an explain portion. And if you're doing multiple choice, then the explanation doesn't matter. You just need to be sure. But very rarely are they going to give you one of these not defined numbers if you're doing a multiple choice. Okay. Again, like I said, I know I'm kind of teaching you towards the test, but our goal here is not an A. Our goal here is a 5. All right. Now, this is where we start entering with the idea of limits. When we're doing limits, our whole idea with limits is we're just saying how close can we get to something without actually using it or without actually touching. So, for example, when we're doing asymptotes, you're not ever allowed to touch that point, but when you're graphing, you get pretty doggone close. Like, for example, if you have like a horizontal asymptote, like your end behavior here, you might get really, 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 really close. And the further you go on, you don't ever flatten out. You always get closer and closer and closer. And if your asymptote's at 1, you might not ever touch 1, but you might be at 1.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 and all of these types of numbers, the closer you get to one, that's what's kind of going on. Now, with limits, we're doing the exact same thing. We're saying, I'm going to get as close as I can to this number without actually using it. That's why it's called a limit. How close could I get to something? And we kind of think of it like asymptotes or dividing by 0. When we're dividing by 0, it just breaks the math at this point. But when we divide by 0 or divide really close to 0, we know that our number gets really, really big, right? That's how we get these vertical asymptotes sometimes, where we have lines that look like this, right? Where we say, okay, I know that it's never gonna, I can't divide by 0, but I can get pretty doggone close. Yikes, sorry, I'm hiding that behind my face. But that's kind of the whole idea with limits. We're saying, how do I get really close to a number without actually using it? And the way we do this is with this limit notation. Now, just copy this down. I'm going to notate on this to show what the different parts are. But this is read as the limit of g of x as x approaches n. I should write that out. Sorry, let me write that out. This is read as sorry, I read it backwards the first time, but it's read as the limit as x approaches n of g of x. In layman's terms, this is described as what happens if x gets really, really, really close to being n, but technically isn't actually n inside of my function. What happens as x gets really close to being n, but is not actually n inside of my function? Okay, this part here, obviously this is read as limit. This is your variable. This is your independent variable. This here is your number you're going to. It's your number you're testing, kind of. This arrow here just means approaching. It's x approaches n, and then again, this is your function. So for example, I could write something as limit as x approaches 1 of x plus 3 or something like that. And this says, what happens to my y value? What happens to my function as x gets closer to 1? And as you guys kind of might be able to figure out, well, it's probably going to get really close to 4. It's not going to be 4, but it's going to be really doggone close. If x is like 0.99999999999999999, it's going to be 3.99999999999, so on and so forth. It just gets really, really close. But again, the whole idea with limits is we're saying, what happens when I get really, really, really close? Now, the reason why this might seem disjointed from what we were learning about previously is because it's like, what the heck does this have to do with slopes? But the reason why we have this is we're saying, remember, we're taking secant lines, right? And what happens as my secant lines get closer and closer together? It gets more and more accurate. So the whole reason why we're kind of using limits here is we're saying, okay, how do I make these secant lines as tiny as possible? How do I make my intervals as small as possible 1 to 1.001 is okay. 1 to 1.000000001 is better. 1 to 1.000, so on and so forth. The closer you get it to 0, the smaller that your gap gets, the way more accurate you get to instantaneous velocity. And that's kind of what we're building here. We're building this method of us being able to work with it, and the way we're doing it is by inventing this idea of limits and looking at how they work amongst themselves, how their rules work, and all of these things. That's kind of the goal. That's how we're going to pull it in all together. Now, again, there's a lot of rules in it. There's a lot that kind of works together. So that's why it's going to take us an entire year to get really good at limits, and then eventually derivatives, and eventually something called integrals. But again, it's all under the same goal of rate of change and, like rate of change, and how do we undo that? Questions? We're doing okay. Idea of limits. Doing good. Excellent. I do appreciate you guys messaging out that you guys are doing good. It helps me pace myself. I know I have a tendency to talk a little quickly sometimes, so this just really helps me out. Excellent. Okay, moving on. So, graphically, let's kind of talk about limits and how limits exist. Now, sometimes limits exist when we're working with like functions like I showed you earlier, but a lot of times it'll pop up graphically. So I'm going to show you how to work with these back and forth. Since I'm going to be using that graph, I'm going to make my face disappear for a second. So now, this is the definition of limits existing. You can tell a limit exists if you can tell where the number is quote unquote supposed to be. Limits don't actually look at the actual number. All we're doing is we're saying what happens when I get really, 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 really close. Now let me show you an example. Now I'm going to zoom in over here, and let's look at 3. If I were to plug 3 into this piecewise equation, technically, what is, now assuming this is g of x, right? What is g of 3 technically going to be? If I plug in 3, what's the actual number I get? It's not here. It's not here. It's wherever it's filled in. So g of 3 is going to be what? 3, right? And so because of that, that's what g of 3 is. However, I'm not looking at that. I don't care. All I'm saying is what happens when I get really close to it. Now let's look only at this left side over here. As I get closer and closer to 3, what's my number getting closer and closer to as I get closer and closer to 3? My number is getting closer. My g of x is getting closer and closer to 1. Whereas if I'm coming from the right side, my g of x is getting closer and closer to 2. Right? If I'm coming from the left side, it looks like it's going towards 1. If I'm coming from the right side, it looks like I'm coming towards 2. And if I'm looking at it right in the middle, it's not even either of them. So because of this, we say the limit does not exist. So again, our limit exists if I look from the left side and the right side, I can tell where it's supposed to be heading to. If I can't, then we just say the limit doesn't exist. So for example, if I were to read this over here, it says find the limit of limit as x approaches 2 of g of x. The limit as x approaches 2 of g of x. So now looking over here, we're seeing what happens as I get closer and closer to 2. So as I get closer and closer to 2 from this side, I'm getting closer and closer to 0. As I'm getting closer and closer to 2 from this side, I'm getting closer and closer to 0. So what is my limit going to be as I'm getting closer and closer to 2? My answer is 0. My limit is approaching 0. So if I said, what is the limit? The answer is 0. I'm approaching 0. That's the number I'm heading to. Any questions on this? We're doing okay. Kind of makes sense. Okay. Wonderful. Again, if you have questions, just throw it up there. Even if I go on past it, if you type it up there, I can always swing back to it. So that'll be nice. Okay. So moving on. let's see the limit as x approaches 3 of g of x. The limit as x approaches 3, as we said, I don't know what it is from the left, I know what it is from the left, I know what it is from the right, I know what it is in the middle, but since they're all going to different things, I really have no idea, so this is just going to be, it does not exist. The limit does not exist. It just, I have no idea what it is, because it's just so confused. Finally, the limit as x approaches 0 of g of x, we're looking at this point over here, at 0. So at 0, from the right side, we're approaching towards 2. There's nothing here, but on the left side, there's really kind of nothing either. There's that huge drop off. So what do you think it's going to be? Type it out in the chat really quickly. You don't need to break up into your little groups. We're going to do that next. But in your chat really quickly, what do you think the limit's going to be as x approaches 0? Okay, interesting. So the answer is does not exist. The reason why it does not exist is if I'm coming from this left side here, what happens is I'm getting closer and closer to 0, right? As I'm getting closer and closer to 0, my y value's just nosediving all the way down. And so because of that, we're always looking from the left, we're always looking from the right. Even if there's that drop off, we always look from the left, we always look from the right. Does this sort of kind of make sense? All right, wonderful. So basically, that's what the limit is. We're seeing, all right, check from the left, check from the right. It's like look both ways before you cross the street, and then make sure you're heading towards the same spot. Any questions on this? Yes. No. Yeah, you have to be able to see where it is because you got to check from the left. You got to be able to check from the right. Yes. So Donovan, the limit can only be defined if the functions meet at the same point, right? Because just like we talked about this one at 3, if I know what it is from the left, I know what it is from the right. It's just because they're not the same, I can't tell you which one it is. I can't guess where it's going to. Michaela, is the limit where the two lines meet? Yes and no. And this is actually what I'm going to hit next. So basically, what if I took the limit as x approaches -1 of g of x? Okay, that's this point right here. And then you know that the answer is 0, right? It doesn't need to be where two separate lines meet. Like, that's just where it gets a little tricky. But you can still definitely do it for all of these other numbers. You can take it at 0. You can take it at like -1.5. You can take it at like -1 or something like that, right? Any of these work. You just got to say, okay, where's it coming from? From the left side, I'm heading here. From the right side, I'm heading here. From the left side, I'm heading here. From the right side, I'm heading here. And again, you're not looking at it from far away. You're saying when I get really, really close. So for example, if I said, what is the limit as x approaches 1 of g of x? All I would do is I would just zoom in here. I'd say, okay, let's see, 1 is right around here. So from the left, I'm heading to about here. From the right, I'm heading to about here. That looks like about 1. So my limit is equal to 1. Does that sort of kind of make a little more sense? Again, it's not like it doesn't need to be two broken pieces meeting up together. It could be a smooth curve. And you're just seeing, okay, from the left side and the right side, am I going to match up towards the middle at the same point? Absolutely. So like this point over here at -1, this is a smooth function, right? Like it's there's no breaks, there's no jumps. I just go all the way down. I can find what the limit is on there. But generally it's really easy because obviously all you do is you just plug the number in and it's really easy to figure it out. But for something like like this, where there's this bend and there's this piecewise, that's where it gets a little more tricky, and that's why those are the questions that pop up more. But don't think you only have to find where you have those two things that like piece together. Does that make sense? Okay, any other questions? Oh, Jing asked a question. Will we be able to find a limit with only one side of point? No, you have to have two sides. You have to have the left side, you have to have the right side. They have to be coming towards the same side. So for example, and that's a really good question. So for example, if I have a graph that looks like this, I start here and then I just go this way. And I say, what is the limit at 1 or something like that? I can't take the limit because I know where it's coming from the right side, but I don't know where it's coming from the left side. There's no left side. So because there's no left side, I just cannot figure it out. So to really, really kind of put it together but not be very mathematical, we're saying what happens if I go to, or like, what's the number going to be if I, oh good lord, what's the number going to be if I go from the left side and the right side? Will they be going to the same number? If they're going to the same number, you can find the limit. If they're going to different numbers, you can't find the limit. If one exists and one doesn't, you can't find the limit. Okay, how we doing? Doing okay? Can I move on? We good? Excellent. Good. All right. So now this is where it gets a little bit more interesting. What is the limit as x approaches n of, I don't know why I put g of x is f of x. Limit as x approaches 1 of f of x. Okay, that's the first question. Limit as x approaches 1 of f of x. The second question is going to be, does the limit x approaches n of f of x, I don't know why I put g of x, stupid. Does this limit exist for every point on the interval from -2 to 2? Sorry, I should have checked this. This is -1, yeah, from -1. From here to here, from -1 to 2, does the limit exist at every point? Sorry, my bad. I just didn't proofread this. Okay, so 2 questions that I want you to do. Again, go back into your groups, see if you guys can figure it out. This is my last slide, then we're done for the day. All I want you to do is figure out, number 1, what is the limit as x approaches 1 of this graph over here, of f of x, as x approaches 1. Secondly, does the limit exist for every point on the interval -1 to 2? Okay, good luck. Figure it out. Jump in your groups. Take a picture before you go. Post it up. Or I guess I can screen cap it for you guys as well. Yeah, I'll screen cap it and I'll post it in the chat. Yes, sir. Mm-hmm. No, it's not saying is the limit the same. It says does the limit exist, meaning can I find the limit as x approaches 0 or zero point 0.1 or 1.5, right? It says does the limit exist, right? Remember, all of this is saying what's the limit and does the limit exist, or does the limit exist, and if so, what's the limit? Make sense? Yeah. Mm-hmm. Oh, you're gonna speak for us? Thank you, Michaela. Oh, Brian's speaking too. Yo, don't hate on my laugh, man. That's not cool. So mean. It's okay. I'd be very careful about teasing someone's laugh because the reason I laugh like that is straight up because Double Lift used to laugh like that, and we used to tease the hell out of him for laughing like that. And like he laughs like, and then like it just kind of happens. So be careful who you tease about their laugh because it might stick. All right. No worries, no worries. I'm just playing. I'm just playing. I'm not sure if you can tell. Don't really care. All right. All right. So it looks like most of us are kind of finishing up. Okay. Does anyone want? All right. So again, same thing. Type it out. Whoever's group you're in, just type it out. And I'll call on you guys to explain. So just type in your answer. There's two questions. Number one, what's the limit as x approaches 1? And then secondly, does the limit exist for every single point? I don't know Double Lift. I just know his I just know about him. Interesting. Okay, Sandra, can you explain for us really quickly why you think it does not exist and no? No worries, no worries. No, no. Mm-hmm. 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 Okay. Okay. And then no, go. No. Hmm. Okay. All right. Now here's the thing. A lot of you guys are saying, "Wait, I didn't see the dot," and that's because you guys probably were looking at Chewan's, uh, instead of the one that I put. But it actually doesn't change the answer because there's something that I put on here that I did mention once, and then it says limits do not look at the actual number. Right? I'm never actually looking at f of 1. I'm saying I'm getting really, really close, but I'm not looking at F1. No, 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 it's not your fault. That's how I was zoomed in, but then that's why I uploaded it after. That's why I normally take down my face. But when you're doing this over here, it really doesn't matter because, again, what limits are saying is coming from the left, what's it getting close to? Coming from the right, what's it getting close to? But what it says here is limits don't actually look at the number. The goal of limits isn't to figure out what F of 1 is. It's saying from the left and the right, what number am I heading closer towards? Does that sort of kind of make sense? So the answer for this is 2. It is 2. The limit should be 2. Because it doesn't care where the actual number is. So even if there was a dot, even if there was no dot, it doesn't matter. It's just saying that I'm heading towards 2 from the left and right. Because I don't care about what the actual point is. Limits just say I'm getting really, really doggone close. Okay, doing okay. Got a few, yeah, we're doing goods. But again, main reason why I'm again beating this like a dead horse, beating this like a dead horse is just because I really want to make sure that you guys understand the idea behind limits. We're not actually looking at the number. We're just getting really doggone close. We're just saying, okay, what's it getting close to from the left and right? That's the important thing. Not the number itself. Just we're getting really close. The reason why the dot is being ignored is because it's a middle child and no one cares about them. Okay. No, sorry. In all seriousness, the reason why the dot's being ignored is because, again, all I'm saying is what's happening as I'm going to the left, as I'm going to the right. Limits only look at trends. It doesn't look at what's actually happening. If I wanted to know what this dot was, I would have said, what is f of 1? That's what this says. But the limit says what happens when I get close. Again, we're just saying what happens as I get close to it. What are the numbers trending? What's the trending numbers going to be? You're just looking at your pattern. Really, that's all you're doing. Like as I'm coming in from the left, I'm saying, okay, my pattern's getting closer and closer and closer to 1, 2. Okay, as I come up here, my pattern is getting closer and closer and closer to 2, so it should be 2, but it turns out that it wasn't. But I don't care because the limit doesn't say what's the number. The limit says what's the pattern going towards. It's okay. I'm the middle child too. That's why my sisters are successful and I'm a math teacher. Questions? Okay, I'm going to be getting to that in just a second, but any questions on the first one before I move on? Because this one was very specifically set to like drill in your brain that we don't touch the actual number. We just get as close as we can. That's the important part. Context is key. Like if I were to say there's something called continuity that we're getting to next week. The dots matter in continuity, but when it comes to limits, again, limits just say what's the pattern? Where's it getting closer to? Okay, if you have any questions or need clarifications, feel free to type it out. We're going a little bit longer than I was hoping for, so I'm just gonna be wrapping this up with the answer to the second question. But again, if you have questions, feel free to answer it or ask it. Then I can always clarify later on. If after like other people leave and I can just talk with you guys individually, that's totally fine. So here, it says, does the limit as x approaches n for f of x exist for every point n on the interval -1 to 2? The answer is no. The reason why is because basically what you're kind of doing is you're looking, you're saying, okay, can I find the limit here? Yeah. Can I find the limit here? Yeah. Can I find the limit here? You're basically saying, can I find the limit at every single one of these points? And it looks pretty good, but what about here? Where there's this dot. If I start here and I move either to the left or to the right, I'm totally all off on my own. I can't take the limit to anything left or right from here, even if it's something like 1.0001, because if I take 1.00000000 and I get as close to 1 as I can, if I'm looking starting at 1 and I'm going from this point over here, they're going to different numbers. One of them is going to be going towards -1, the other one's going towards 2. So basically, if you're trying to see does the limit exist for an interval, this is not really a normally asked question. I just wanted to see what you thought about this. This is a continuity problem, and we'll cover it in continuity more. But I just wanted to see what you thought. But no, technically it doesn't work because there's this little break here, so I can't find the limit coming from the left and the right. That was a little bit more of a, I just want to see how you'd react to it. Again, like I said, I will cover this more in continuity, so if you're like a little confused still, don't worry about it. I'll cover it next week, I promise. Just keep this in the back of your head. Okay, any questions? Does it matter that from x equals -1 going to the right we approach y equals 0 and not y equals 2? No. The reason why is because, again, remember just like when we did our it's patterns, right? So we're saying, okay, first I'm starting towards 0, but as I'm getting really close to 1, y is approaching 2. It doesn't mean all of my y values need to be 2. It just means as I get closer and closer to 1, I'm approaching 2. And again, the whole idea here is because we're saying what is my function going to be as x approaches 1. And again, the whole idea with limits is we're saying we're getting really, really close. So if you're taking it at 1, you're taking it too far away. Later on in the future, if you're taking it at 1.5, you're taking it too far away. You're taking it at 1.001, that's still too far away. You got to get really doggone close. Like, that's the whole idea with limits. We're saying as I'm getting super, super, super close, like 1/1,000,000th. Okay. Any other questions? Good questions so far. Great questions. Great questions. Okay, if not, then that's it for today. I will see you guys on Wednesday for our next lesson. I'm so sorry. I normally would have had the homework now, and I would have said, have fun, play around with the homework, do what you guys need to. But unfortunately, I was just having, like, even if you can, I'm sure you can kind of tell on this graph looks different from this graph, looks different from previous graphs. I had to, like, find graphs online because for some reason my computer just wasn't letting me graph stuff out nicely. So I'm going to have to adjust that. I'm working on your packet. Your packet will be up by tomorrow, Wednesday at the very latest, and it'll have about a week and a half, 2 weeks worth of work. As far as study dates, I'm not going to be holding a study date tomorrow, but most other days I will be hosting study dates. I posted it on the announcement. Feel free to check that. The reason why there's no study day tomorrow is since you don't have a homework packet, there's nothing for you to work on really. Please take advantage of these study times because, again, you're not getting a lot of questions and answers here. You're getting a little, but not a ton. So it's good for you to practice. Ask me questions as you guys go. So it's basically like a study session. You guys can just be in the different groups. I'll probably be at my computer, like just working on some work, or honestly might even be playing Animal Crossing or something. And then if you have a question, I'll just pop in and help you guys out. But again, that's going to be time for you. It'll be like a study group time. So I have all of those posted online. The homeworks will be posted both on the Weebly as well as the Google Classroom, and then I'll post like with dates and instructions and all that fun stuff. Any other questions? Do you only have one class a week? We'll have 3 classes a week for now: Monday, Wednesday, Friday, 2 hours a pop or so. I'm probably gonna reduce it, and then I'm gonna go maybe 2 classes a week. So we'll cover 2 big lessons a week, and then we'll just really kind of work on practice, and then it's just get your homework packet done for the week. So it'll be like 2 mandatory sessions, and then the rest will be, please try to come in, see me when you can if you need help for the homework, or at least come in one day. I'll work on that a little bit more. I'm still kind of pacing it out, and today was really helpful for me. It kind of showed me how you guys work, how this works together as a whole. So if you have any comments, if you guys can private message me like what you thought about the class after. If you want to put me on blast in the general chat, that's fine as well. But again, like I said, the more information I have about how you felt about the class, things you thought could have been better, if you thought it could have been a lot more streamlined, I mean, I know I definitely could have made it a lot more streamlined. So give me more information. The more information I have, the more I can tailor the class to you guys, and we can work around our schedule. But no, you will be having 3 classes a week this week: Monday, Wednesday, Friday. And then next week, I'm probably going to take it down to 2, where it's 2 lecture days. And then I'll have 4 days of pick your poison, just come in to study at least one of them. Questions? How would you submit your homework? There's a lot of different ways for you to submit your homework. Most likely, though, what I want you to do is just take a picture of it and send it to me. Honestly, it's not the end of the world if you're not submitting your homework, because I'm not necessarily grading it. But what you should be doing, though, is as we're in those study sessions, you should be saying, hey, Mr. Morimoto, this is what I got for number 1, number 2, number 3, number 4. How'd I do? And I'll say, okay, you got number 3 wrong. Let's work on that together. So that's kind of how it is. It's more like an honor system thing. But if you want me to look it over, which I think is a good idea, then you can always submit through Google Classroom by either taking a picture, or like if you have a tablet, you can like write on the tablet or whatever, things like that. Okay, if you guys have no more questions, if you guys have questions, I'm still going to be on here. I'll be on here for about another 10 minutes or so to field any questions. If everyone leaves, then I'll just leave. But if you need to leave, if you want to head out, you have no questions, thank you guys so much for coming. Again, if you guys can, please shoot me a message or put it in the general chat, or the general chat, just what you thought about the lesson as a whole, how I can adjust it, because I know with distance learning, honestly, I'm still trying to figure it out, how to make it as effective as possible. I know it's a little difficult being engaged the entire time, so feel free to let me know. Like I said, I'm not going to be able to do everything, but the more information I have, the easier it is for me to kind of adjust things. So again, thank you guys so much. If not, you guys can stick around, ask me questions. I'll still be on here, but you guys are free to leave. But again, just please try to send me a feedback, like it could be like quick, but try to honestly think. I'd rather you like think about it and send it to me tomorrow than to just send me it was all right today. Because I do take this seriously, and I do try to adjust the way that I run my lesson and like the video and the stream. Okay. If not, like I said, see you guys later. Thank you guys so much for coming. I'll see you guys on Wednesday, same time. I'll post up on the Google Classroom the homework packet, as well as post an announcement once that's up on Discord. Okay? See you guys later. What happens if you get the correct answer but the process? Okay, if you get the correct answer and the process is completely wrong, again, you can always send me questions and stuff like that. You can always submit. That's why when you're doing homework, you should be inside of you should be coming to one of the study sessions and talking to me. You should be able to. You should be saying, "Hey, Mr. Marmoto, how do I do this one here, this one here?" That's why I'm not like taking a ton of time to like just take it and look at it. I'd rather work with you and do it with you than have to just look at like 30 sets of papers after the fact, especially with how this is set up. So that's just me personally. But yeah, I would hope that you don't do that. Like, that's why I'm not posting up answer keys necessarily. I'm probably gonna end up posting answer keys, but the chances of you getting it totally wrong, the process totally wrong, and getting the answer right is pretty small. Kind of. Later on in the year, there's a good way to guess. Just take the derivative, set it equal to 0.